Hello, dear students. So let's start our next topic of the chapter electric potential and capacitance. Till now, we have seen the topic one, that is electric potential. In that, we have seen already that what is electric potential and what is potential energy of a system or of a particle. Potential electric potential difference also we have seen. Then we have also covered the dipole part of like what is the potential energy of dipole, and also we have like seen the potential energy of a system of various charges. So now we will see the next topic of this, that is dielectric and capacitance. Okay. In this topic, we are going to learn about the characteristic properties of conductors and insulators. Also, we will go through the concepts of capacitors and their combinations. So in this chapter, we will see what are conductors and insulators, and also we will see the uh, combination of capacitance. That is very important for you. Okay, so let's move. First topic is what is conductors and insulators. So we have to discuss this part, that what are the basic differences between them. So conductors are what? Conductors are the materials through which electric charge can flow easily. Okay, conductors are the material through which electric charge can flow easily because they have plenty of what? Free electrons. Most of the metals are conductors of electric charge. So metals are what? They are conductors of electric charge. Silver is the best conductor of electric charge. So you have to remember that silver is the best conductor of electric charge. Okay. Under electrostatic conditions, the conductors have following properties. So these are the some properties of your like conductors, that inside a conductor electrostatic field is zero. If you have like here a conductor like that, okay, inside this your electric field will be what? It will be perpendicular to the surface, but it will be zero inside it, because here it will be like shielding effect inside the conductor. This I already covered in the first chapter. You can see that if electric field are like coming here, so it will generate inside opposing and equal electric field, which cancel out the original electric field, and here the net electric field will be what? Zero. Okay. So that is why there it is also said here that inside a conductor electrostatic field is zero. Okay. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. So this also I have told you that at the surface of your conductor, the electric field lines are what? Perpendicular to the surface. Okay. So what is the next point? Yes. The third is that the interior of the conductor can have no excess charge in the static situation. So you can see that if interior of any conductor is there, so it has no excess charge because the charge move to the surface of the conductor. Okay, they reside on the surface. That I already told you in the first chapter. You can also see that. Okay. Fourth property is electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. It is obvious that because there is no electric field inside the conductor, so there should be electrostatic potential constant throughout the volume of the conductor, and should have the same value inside on its surface. Okay. Fifth property is surface charge density of a conductor could be different at different points. So this is also obvious because you can see that conductors have like, if they are not uniformly in their shape or size, so there can be surface charge density which vary with the shape and size also. If they are uniform, then your surface charge density is also uniform there. Okay. So this we will see in some examples. Okay. So I should like clear the drawing here and then move forward. Okay. So here it is written also that what is electrostatic shielding. The phenomenon of protecting a certain region of space from external electric field is called what? Electrostatic shielding. We know that inside a conductor electric field is zero. So to protect some instruments from external field, they are enclosed in hollow conductors. So that is also like application of shielding effect, that if you want to uh, uh, give protection to some instruments from external electric field, we can place them or enclose them in a closed hollow conductor. So inside the conductor, there will be no electric field or no effect of electrostatic like field only. Okay. So what are insulators? Insulators are the materials through which electric charge cannot flow. Example: glass, rubber, wood, etc. So you have already seen in the smaller classes, 10th or ninth classes, that insulator are the materials through which electric charge cannot flow because they have very less amount of free electrons, and free electrons are only responsible for what? For your conduction or of electric or heat energy. Okay, so that is why here you can see that your these materials are not good conductors of electricity and also heat energy. Okay, so these are examples of some insulators that are like glass, rubber, wood, etc. Okay, insulators are also called what? Dielectrics. So this is very important for you because this term will be used in future many times. Dielectrics is the term used for what? This is used for insulator only. When an electric field is applied, induced charges appear on the surface of dielectric. So when you apply an electric field, induced charge appear on the surface of dielectric. So there is some induction of charges on the surface of dielectric, not on the whole body or whole volume, but on the surface of the dielectric. Hence, it can be said that dielectrics are the insulating materials which transmit the electric effect without conducting. Okay. So it can also be said that dielectrics are the insulating materials which transmit the electric effect without conducting. So that is why they are called like insulators. They have insulating property. So they are called what? Insulating materials, and that can transmit the electric effect without conduction. They have not the property of conduction, but they have the property of insulation. Okay. Insulation means electric effect due to insulation effect. Free charges and bound charges inside the conductor. So I already told you about what are the free charges. Let's see in the detail. In metallic conductors, electrons are the charge carriers. Okay. So like if you have metal here, if you have metal here, so electrons are the charge carrier here. Like you have electrons which are you see in the atoms of this. This is an atom of a conductor. So it has electrons inside them. Okay. They are revolving like this only. Okay, like this. So these electrons are the what? These are charge carriers. In a metal, the outer valence electrons part away from their atoms and free to move. So this electrons, like the outermost, like this one, if this is outermost shell, then these electrons are very much free here, and they are like responsible for conduction. So these are called what? These are called as free electrons or conduction electrons. The electrical conductivity of a material depends upon the number of free electrons present in it. So it is obvious thing that if you have number of free electrons more, then there will be more conduction throughout the your conductor. Okay, and its electrical conductivity of material will be higher. Okay, so I assume that you got this point. Let's move forward and see the next thing. Materials which have high number of free electrons are good conductors. So materials which have high number of electrons are called what? Good conductors of electricity. And which have less number of free electrons are bad conductors. And obvious thing is that if a material has less free electrons, then they are called what? Bad conductors of electricity. When an electron leaves an atom becomes positively charged ion. So if an electron is leaving the atom, atom because atom become what? Positively charged ion because it has excess of protons inside there. Electron has been removed, so it must have excess of protons inside this. The positively charged ions and bound electrons remain held in their fixed positions. Okay, so positively charged ion and bound electrons will be held in their fixed position and are called bound charges. So if this is your nucleus inside the atom, so this has protons. This is called what? Bound charges because they are not like moving freely inside the atom. and these all electrons which are inside your shell, means that valence shell is like outermost valence shell, this is, and these are like your inside cells. So these inside cell electrons are also not free to move, so these are also called bound charges. Okay, these are called bound charges collectively. So I will move forward now. Let's clear this part. Dielectric and polarization. So dielectrics, we have already talked about that they are insulators, or they are non-conductive substances. In contrast to conductors, they have no or negligible number of free charges or charge carriers. So they have what? They have like negligible number of free charges or like charge carriers. Okay, because they are insulators, so they have negligible amount of charge carriers. In a dielectric, under the effect of an external field, a net dipole moment is induced in the dielectric. Okay, so if you have like a dielectric is there, and if you apply any electric field here, external electric field, like this is E naught, which is applied here, see in the figure, which is external, this is external electric field. Okay, a net dipole moment is induced in the dielectric. So there is a dipole moment term is induced inside the dielectric. Why? Because you can see that the electric field has the direction like this only. So it will move from positive to negative. So here you have like positive charge on the surface of this, and due to this, in the inside there will be negatively charge induced due to this only. So similarly for this surface, you have negative, and then you have positive induced here due to negative charge, and here there will be negative charge induced on this surface. Okay. So, due to molecular dipole moments, a net charge appears on the surface of dielectric. So, there is a net charge appearing on the surface of dielectric. Okay. These induced charges of density minus sigma p and plus sigma p. It means that this has plus charge also and minus charge also on the surface. So, plus charge will represent plus sigma p, and minus charge will represent minus sigma p. Okay. This will produce a field opposing the external field. So you can see here that you have an inside electric field induced here from plus charge to this minus charge. So this will be induced like this, induced inside the dielectric. Okay, which is opposite to the external field. So it is also opposite to the external field, that is E naught. E naught is from this direction, and E in is like in this direction. So this is like both are opposite to each other. Induced field is lesser in magnitude than the external field, and here induced field is lesser in magnitude because you can see that it only generate electrons on the surface here, but electric field outside it is like on in the whole space. So this is like more powerful field. Okay, so the field inside the dielectric gets reduced. No, so you can see that inside the dielectric there are two types of electric field present. One is E inside and another is E external. So if you calculate the net electric field inside it, it will be lesser than E naught. So E naught minus E in must be lesser than E naught. So there inside the conductor, and so your dielectric, inside your dielectric, you have lesser magnitude of net electric field than E naught, or than external electric field. So its magnitude is given as mod of E naught minus mod of E in. Okay, where E is the resultant electric field in the dielectric. Okay, so it is the like resultant electric field inside the dielectric. Okay, so here E naught is external field between the plates, and E in that we have already seen that they are what representing. And then dipole moment is developed by external field in either case, whether a polar or non-polar dielectric. So you can see that there is an external field is developed inside the uh, like external or internal field, you can say, is developed inside the dielectric, whether it is polar or non-polar. Because of induction, there is like development of electric field inside the dielectric. Whether it is polar or not polar, it not depend on that. Okay, so I will clear this all diagrams and move further. Dielectric constant. Okay, so this we have already seen in the first chapter. The ratio of the strength of applied electric field to the strength of the reduced value of the electric field on placing the dielectric between the two plates is called the dielectric constant of the dielectric medium. It is also known as relative permeability or specific inductive capacity and is denoted by K or epsilon R. So this we have seen because if you apply electric field inside any dielectric. So, applied electric field on the strength, there is a ratio of strength of applied. So, K is what? E naught by E. Because E naught is greater than E, so dielectric K must be greater than 1. Okay. This is was nothing but only a term which define a ratio of E naught by E. And we have already seen that what is E induced and net net electric field inside the dielectric and E naught is external electric field. So the ratio of the both is what? Your dielectric constant. This is also called what? Relative permittivity or specific inductive capacity. And it is noted by epsilon R also. The second term is polarization, P. So polarization is denoted by capital P. What is that? The induced dipole moment developed per unit volume in a dielectric slab. Okay. On placing it in the dielectric field is called polarization. So this term, like polarization, is used very rarely in your syllabus, but it is you have if you have a dielectric slab like this, and you have developed here like minus charge is inside, and here plus charge here. So you have like here minus to plus charge. Okay, yeah, this is your dipole moment inside the this your dielectric. So if P is the induced dipole moment acquired by an atom of the dielectric and N is the number of atoms per unit volume, then polarization is given by P is equal to N into P. Okay. So what is the polarization value? P is equal to number of atoms per unit volume. So this N is what? Capital N is number of molecules or number of atoms per unit volume. Okay. So this you must remember that capital M is small n by capital V, where small n is number of atoms of your dielectric, and this is like capital N is your number density only. Okay. So here you have P is equal to N into small p. P is the induced dipole moment. So P already has covered that what is dipole moment. So this is the value of capital P only. Okay. So what the induced dipole moment P acquired by the atom is found to be directly proportional to the reduced value of electric field, and it is given by P is equal to alpha epsilon naught into E. Okay. So if you have like induced dipole moment inside the atom, it is directly proportional to reduced value. So this small p is directly proportional to what? Capital E. That is the induced electric field inside the dielectric. Okay. So P can be written as equal to alpha times epsilon naught. Alpha, this is alpha times epsilon naught into E. Okay. So here alpha is what here? This alpha is called proportionality constant, and this is also called atomic polarizability. Okay. See here, it is called as atomic polarizability. So you have to remember this point that what is alpha here. Just a second, we will remove these drawings. So now we will see what is electric susceptibility. So these terms will be used in magnetic materials also. So we will see these terms here. Okay. So the polarization density of a dielectric slab is directly proportional to the reduced value of the electric field and may be expressed as capital P is equal to xi times epsilon naught into E. So you can see here that there is similarity between this induced dipole moment and this is your polarization density of a dielectric slab. So this is capital P here. Okay. So this capital P is equal to what? Xi times epsilon naught into E. Okay. So this is also proportional to your extra electric field induced inside the dielectric, and there is proportionality constant here, which is xi, and it is called what? Electric susceptibility of the dielectric slab. It is a dimensionless constant and it describes the electrical behavior of a dielectric. So it will show what? Electrical behavior of a dielectric only. Yes, it has different values for different dielectrics, and it is like dependent on material property, so it is different for different dielectrics. For vacuum, your xi value is 0. Relation between electric constant and electric susceptibility can be given as. So here is the relation between your dielectric constant and electrical susceptibility, that is equal given by k is equal to 1 plus xi. So you have to remember this formula. This is used widely. So this is like important for you. K is equal to 1 plus xi. Okay. So this is like relation to dielectric constant and susceptibility. Dielectric strength. The another term is dielectric strength. The maximum dielectric strength that dielectric can withstand without breaking or breakdown of its insulating property. Okay. So suppose that I apply any external electric field, and dielectric is like not losing its insulating property. If you increase the electric field, external electric field very much, then it can lose its insulating property and become permanent type of another semiconductor or like conductor material. So it will withstand its original property. So till that last larger value or last value, your electric field value is what? It's called dielectric strength. For air, it is about 3 into 10 power 6 volt per meter. So there is no breakdown till here. Okay. This is your limiting value for air. Now, we will see that what are capacitors and capacitance. So a capacitor is a system of two conductors separated by an insulating medium. Okay. So you have already seen in the fans or like electrical instrument that there is a plate like structure inside it, and it is called what? Your capacitor only. It stores very much charges and helps in the initial motion of your electrical gadgets. So that is why they are used. Okay. Like if you need initially very much high power or high energy, then your capacitors are used only. So this is a load separated by an insulating medium. So the conductor have charge plus Q and minus Q with potential difference V is equal to V1 minus V2 between them. Okay, so suppose that here are two spherical conductors. Conductor 1 is there, which has V1 potential and capital Q charge. And similarly, conductor 2 is there, which has symmetrical distribution minus Q charge is there, and V2 is the potential here. Okay. So the electric field in the region between the conductor is proportional to the charge capital Q. Inside them, due to the attraction of plus charge and minus charge, there will be an electric field in this region also. Okay. And this is proportional to charge, because if the charge is very large, then the electric field intensity will be higher. If the potential difference capital V is work done per unit positive charge in taking a small test charge from the conductor 2 to 1 again the field. Okay, then V is proportional to capital Q and the ratio Q by V is a constant. So what is your capacitance actually? Like if you have to move a positive charge, unit test charge from your conductor 2 to conductor 1 against the field, then V is proportional to Q. Okay. So like you have to move a test charge from this to this surface, you have to do some work due to external electric field. So that work done is your like the term associated with capacitance, and your Q will be directly proportional to V here. So Q by V will come as a constant, and this constant is called what? It is called your capacitance only. Okay, so capacitance value is what? Q by V. This is a very important formula for you. So just remember this, and it will be used in the future also. Okay. Now, if the potential difference V is the work done per unit, this I already covered. The constant C is called the capacitance of the capacitor. Capacitance C depends on shape, size, and separation of the system of two conductors. So you can observe here that capacitance capital C depends on what? If the shape of your plates will change, the capacitance value will also change. If size will change, then it also change. And if the separation of the system of two conductors will change, then it will also change here. Okay, so it will depend in the like physical appearance of your physical what is your like your that is your arrangement here. So it depends on that only. It doesn't depend on Q and V here. You can see also, because that is only your quantity. Okay, this is not your giving the value here, like total value it is not giving here. So yes, so we can see that the SI unit of capacitance is called what? Farad. You have to like always remember this thing, that farad is the SI unit of capacitance. Its dimension formula is m minus 1 l minus 2 t4 a minus a2. So you can find it like what is the your dimensional formula of capacitance. So capacitance is what? Q by V. Okay, and Q can be written like I into T, that is current into time, upon your like volt can be written your this potential difference unit is volt. Okay, so just find out the dimension formula here. I like I what here? Your I is can be written as ampere, and this is time. Okay, upon volt is what? Volt is what? If you see V is what? Work done, like work done unit is only of this. Your V has the units of work done upon charge also, because charge is also there here. So if you write the dimensions of work done, so work done has m, okay, l 2 t minus 3, ml to t minus 3 only. Okay, and yeah, ml 2 minus 2, yes, sorry, ml 2 t minus 2. And your charge has the like q can be written as what? It. Yeah, so here you have it multiplied, like it is in the denominator, so it will go here. It will be a square t square. Okay, now just take it above, so you will get m minus 1 l minus 2 t4 a 2. So this is your dimensional formula of capacitance. I hope you got this, that how I have found out the dimension formula of capacitance. So 1 farad can be written as 1 coulomb per volt. So this is the definition of 1 farad. Okay. A capacitor with fixed capacitance is symbolically shown as this. So a capacitor has the symbol of like two plates. Here is your capacitance like symbol, while the one with variable capacitance can be shown as like this. So if you have variable capacitance value, so it can be shown like a cross line with it. Okay. In practice, farad is a very big unit. So farad is very big unit of measurement, and we use in practical cases like its submultiples like microfarad, 10 to the power minus 6 farad, and nanofarad, 10 to the power minus 9 farad, or picofarad, 10 power minus 12 farad. Okay, so these are the units of your practical application of capacitance. So I hope that you got the points till now, which I have told you. And let's move further and see what is the next thing. So there is one example. Let's do this example and see that how it can be solved here. So example says that when 1 into 10 to the power 12 electrons are transferred from one conductor to another, a potential difference of 10 volt appears between the conductors. Okay, so this is like 10 to the power 12 electrons are transferred from one conductor to another, and here is potential difference that appears between the conductors. Find the capacitance of the two conductors. So we have to find the capacitance of two conductors. Given number of electrons and here is equal to 10 power 12. This is the number of electrons here. Charge transfers Q is given as NE. So if the number of electrons are like N here equal to 1 into 10 to the power 12. So if the charges are transferred here, we can write the total number of charge value as what? Number of electrons into electronic charge. This will come equal to 1 into 10 power 12 into 1.6 into 10 power minus 19 only. Okay, so we will get 1.6 into 10 power minus 7 coulomb. So this is your what? Charge transferred, net charge transferred. And therefore capacitance between the two conductors will be what? C is equal to given as Q by V. E is equal to Q by V only. So just substitute the Q value that is equal to 1.6 into 10 power minus 7 here upon your voltage. Okay, so voltage is given here as 10 volt. So just calculate this value, you will get 1.6 into 10 power minus 8 farad. Okay, so this was the answer for this question. You can also write it in other units like in microfarad units. If you write it like what? Just write it like 1.6 into 10 power minus 6 into 10 power minus 2. You can write like 1.6 into 10 power minus 2 microfarad, which is also this also can be written like there only this answer. Okay, now let's move further and see what is your next topic, or if there is any other question we will take it. Okay, parallel plate capacitor. So this is very important for you because in your general application you only use this type of capacitors widely. So parallel plate capacitor consists of two thin conducting plates, each of area capital A, held parallel to each other at a suitable distance small d. So if you have like two conducting plates, each of area capital A, and they are held parallel to each other at a suitable distance small d, then one of the plates is insulated and other is earth. So you can see here that you have one plate here, okay, and the other plate is in like here, placed here, and it is represented by y, and the above one is x, 1 and 2, okay, and this is earth. The second plate is earth only, and there is vacuum between the plates. Also, the medium inside them is vacuum or no medium is there. Suppose the plate X is given a charge of plus Q coulomb. So if I give a plus Q coulomb charge on your plate 1 or X plate, by induction minus Q coulomb of charge is produced on the inner surface of the plate. Okay, Y and plus Q coulomb on the outer surface. Okay, so you can see here, if you have like plus charge on the inner surface, okay, like this charge is given here plus Q coulomb, so you must be getting a similar induction of charge, like minus charge will be induced in the inner surface of second plate or by plate, that is y minus q minus q coulomb. Okay, so this is your minus q coulomb. For and due to this negative charge, there will be plus charge also induced on this surface. Okay, yeah. And here also you will be like getting a minus charge. It is not shown here, but you will be induced getting induced charge here also. Okay. So by induction, minus q coulomb of charge is produced on the inner surface of the plate. Here you can see minus q charge and plus q on this surface. Okay, outer surface. Then the plate Y is connected to Earth. So this is Earth only. So this charge will disappear here because it will make it zero potential due to earthing. So the outer surface charge close to the Earth. That the plates X and Y have equal and opposite charges. So the plates have equal and opposite charges here. You can see also. Okay. Okay. So yes, here you can see that this has plus charge here, but here this surface is insulated. So that is why here you will not get any induction of charge. I have drawn here, but you will not get any charge because it is insulated. See here, one of the plates is insulated. I have not seen this, but it is insulated here. Okay. So in the inner surface, so you will get equal and opposite charges here, like plus q coulomb you will get here, and minus q coulomb you will get here due to induction. Okay. Suppose the surface density of charges on each plate is sigma. So if the surface charge density is sigma for both the plates, okay, we know that the intensity of electric field at a point between the two plates parallel sheets of equal and opposite charges is sigma by epsilon naught. So this we have already covered in the first chapter that electric field at a point inside between the two plane parallel sheets of equal and opposite charges is sigma by epsilon naught, where epsilon naught is the permittivity of free space. The intensity of electric field between the plates will be given by E is equal to sigma by epsilon naught. So this is the formula we have already derived in the first chapter. You can see, or this is coming like E equal to sigma by epsilon naught. The charge on each plate is Q and the area of each plate is capital A. Thus the sigma can be written as what? Sigma can be written like Q by A, small q by A. Or E can be written like what? Q by epsilon naught into A. Okay. Now, let the potential difference between the two plates be V volt. So, if the potential between the two plates will be V volt, so the electric field between the plates given by E is equal to V by D. This also we have covered that E is equal to V by D only. So, here V is equal to ED, okay, by cross multiplying. Substituting the values of E, the value of E from equation 1, we get V is equal to QD by epsilon naught A. So, substitute here your like E value. E is what? V by D. So here you will substitute E is equal to V by D. You will get V is equal to QD upon A into epsilon naught. Okay. So capacitance of parallel plate capacitor is given by E is equal to Q by V. So C is what? Q by V only. So substitute here your V value. You will get Q by QD upon A epsilon naught. So Q will be cancelled out here. You will get A epsilon naught by D. Okay. The capacitance formula is A epsilon naught by D. Okay, this is very important for your parallel plate capacitor. This is your capacitance formula A epsilon naught by D, where epsilon naught value is 10 to 8.85 into 10 power minus 12 farad per meter. Okay, it is clear from this formula that in order to obtain high capacitance, A should be large, that is the plates of large area should be taken. So from the formula, it is also clear that a plate of large area will give you large capacitance value. Okay. And D should be small. D should be small because it is coming in the like your denominator. So D should be small. That is the plates should be kept close to each other. And, like plates should be kept closer to each other for the capacitance value to be higher. Okay, so this was enough for today's class. We have seen many topics today, like what is your capacitance and what are insulators, conductors, type of your capacitors like plate, parallel plate capacitor we have seen. And so I hope that you liked the today's session. If you have any type of doubt or suggestion, you can ask in the chat box. If you want any type of one-to-one session or private session from us, you can also tell us. But thank you for today's session. Have a great day.